And for example 1, we're going to make a graph of the family of functions that solves the following differential equation. And the differential equation is dy dx equals the cosine of x. So 6.1b, example 1, make a graph of the family of functions that solves the following differential equation. And then there's the differential equation. Okay, so first of all, just to recap with some of the vocabulary, why is this called a differential equation? Because it's got a derivative in it. dy dx is in the equation, the derivative is in it, so it's called a differential equation. Okay, then what does it mean to solve a differential equation? Figure out what the original y is. So in this case, it's not too difficult, because the derivative of sine is cosine. But then, of course, you need plus c, right? So this is called a general solution because it's a bunch of different answers. So one of the answers is sine of x plus 1, another answer is sine of x plus 5. So now we're going to graph all of those possibilities. So first of all, if c was 0, it would be sine of x plus 0. So it would look like this. So there's one of the members of the family, sine of x plus 0. And then if it was sine of x plus 5, it would be up here instead. So there's another member of the family, sine of x plus 5. So to be in this family, you have to start out with sine of x, and then just plus any number, right? So another member of the family is sine of x minus 3. So when you graph the family of functions, just graph 2 or 3 of the members of the family. You couldn't possibly graph them all, because there's sine of x plus a half and sine of x minus a half, et cetera, et cetera. So the family is very large. But just graph a few of them, and then you get a picture of what's going on. Okay, so the next one is example 1.5. On your sheet is example 2. We're not there yet. So this is example 1.5. We're going to make a graph of the family of functions. That solves dy dx equals 2x. So if dy dx equals 2x, what does the original y equal? X squared and then plus any c, right? So it could be x squared plus 0, which would look like this. Or it could be x squared plus 3, which would look like this. Or it could be x squared minus 5, which would look like this, whatever. So there's the picture of the family. That might bring up bad memories if I talk about family pictures, right? There's usually a fight, somebody cries. Why? I don't get. I'm not sure why, but it happens. Yeah. Anyway, sorry for bringing up bad memories for you. I think when you're little, you're putting on clothes you don't want to wear. That's the problem. So there's always a fight about that now. Anyway, so there's a picture of this family. This family gets along pretty well. All right, so now we're finally ready for example 2. This is the new thing. We're going to construct a slope field for dy dx equals 2x. So this is something we have not heard about before. This is something we haven't done before. We're going to make something called a slope field. Okay, so if you look at your handout on example 2, you've got a graph there with a bunch of dots on it. So we're going to start with the dot at -1, 2. So there's a dot at -1, 2, so that's what we're going to focus on first. So that's the point -1, 2. And according to this equation, if you want to know what the slope is, you just take 2 times the x value. So if I want to know what the slope is at this point, I just have to take 2 times -1. And 2 times -1 is -2. So now I know that at that point, the slope of the graph is supposed to be -2. So to demonstrate that, I'm going to draw a little tiny line that has a slope of -2. So I don't want it to be at a 45-degree angle, because that would be -1. I want it to be a little bit steeper than 45. So this is not an exact science. So just draw a little tick mark that has a slope that you think is -2. Yes. Okay, so now we're going to go to this point, -1, 1. I guess some vehicle is backing up somewhere. Sorry for the distraction. Okay, so at the point -1, 1, the x is still -1. So the slope is still 2 times -1. So the slope is still -2. So the slope there should be the same as the slope there. So try to draw a line that has the same steepness as that. You probably won't be able to recreate it identically, but they should have, those 2 little tick marks should have the same slope. They should both be -2. Same thing at 0, or sorry, same thing at -1, 0, right? And same thing at -1, -1. Okay, so we got 4 of our points done. Now we're going to move to this dot at 0, 2. Now this time the x is 0. And 2 times 0 is 0, so the slope should be 0 there. So now we're going to draw a little tick mark that has a slope of 0. Same thing here, same thing here, same thing here, right? For all of these points, the x is 0, so that's why I drew little flat lines, because the slope is 0 there. Okay, now moving to the point 1, 2. So that's the point 1, 2. Now the x is 1, right? So to find the slope, we take 2 times 1, and that's +2. So now there I need to draw a little tick mark that has a slope that's +2. And same thing here, right? Because for all of these points, the x is 1. So the slope's not going to change. It's just 2 times 1. So I want it to be the same steepness as that, though. So try to do that. So all of those little lines had a slope of 2. Okay, so that right there, all those little tick marks, that's called a slope field. So when it says construct a slope field, you're just supposed to draw a bunch of little lines that show what the slope is. Okay, now here's the purpose of the slope field. You can see that if I trace this out, so let's say I start here and I go like this, but then when I get here it says to be flat, right? So then I would go flat, and then when I get here it says to go up. So what do I get when I trace that out? A member of the family, right? And same thing here, if I start here, I get another member of the family. So the real purpose of the slope field is to solve the differential equation. When you trace out the slopes, you get the solutions. Now on this derivative, we could take the antiderivative and solve it, right? But maybe there's a really hard antiderivative that you don't know how to do. Then you could make the slope field and trace out the answers, and that would be another way to solve. Okay, so the real purpose of the slope field is, once you get the slope field, if you trace it out, then what you've traced is a solution. So it's another way to solve. You can solve by taking the antiderivative, or you can solve by making a slope field. Okay, now we're going to construct a slope field for dy dx equals x plus 2y. So this is a little bit more complicated of a slope field because it's got an x and a y in it. And also, we don't really know how to take the antiderivative of this. So the only way to solve would be to make a slope field. All right, so if we're going to make a slope field, you got some dots on your paper again. So I'm going to start with -1, 2 again. So I'm going to calculate dy dx at the point -1, 2. So I'm just plugging -1, 2 into that formula. So that would be -1 plus 2 times 2. I just put a -1 in for x and a 2 in for y. 2 times 2 is 4. -1 plus 4 is 3. So that means that the slope at that point is 3. So I need to go over here and draw a tick mark whose slope I think is 3. Again, it's not an exact science, but 3 is pretty steep. So there's a line that I think has a slope of 3. And that's showing that at that point the slope is supposed to be 3. Okay, now I'm going to move to this point, -1, 1. So then I just plug those into the formula. That's going to be -1 plus 2 times 1. 2 times 1 is 2. -1 plus 2 is 1. So then I got to draw a line here that has a slope of 1. So a slope of 1 should be a 45-degree angle, right? So just do your best to draw it 45. Okay, after you show your work for a couple of points, then you can just start. I want you to show your work some, you know how I am, but after you show for a couple, then you can just start plugging in. This is the point -1, 0, right? So 2 times 0 is 0, -1 plus 0 is -1. So the slope there should be -1. So it's 45-degree angle, but going the other way. Then the point -1, -1. So that would be -1 plus -2. So -3. So then 0, 2. 0 plus 4 would be 4. So steeper than that, right? Because that was a slope of 3, so it needs to show that it's getting steeper. Then 0, 1 would be 2. So it gets tricky. It's got to be steeper than that, but less steep than that. Yeah, you could, don't go crazy, but try to do that. So then 0, 0 would be a slope of 0. Zero, -1 would be -2. This was -3, right? So it needs to be less steep than that. 1, 2 would be 5. So even steeper than that. 1, 1 would be 3. 0, 1 would be 2. Sorry, 1, 0 would be 1. And 1, 1 would be 3. Whew. 1, -1 would be -1. There we go. Everybody doing okay? So this is called a slope field because it's a bunch of tick marks that show all the slopes. Okay. All right, for example 4. Slope field for dy dx equals x plus y is shown So look at that slope field that they did, for example, 4. So for example 3, how many points did we do? 12, right? Looks like they did maybe 40 for example 4. So that's a lot of little tick marks showing the slope. Okay, so there's the slope field for dy dx equals x plus y. And what we're going to do is we're going to sketch the graph of a particular solution. Sorry, of the particular solution. So what's the solution for the, when it says solve, what does that mean? Solve for y, find the original y equation, right? And one way to do that would be to take the antiderivative of this, right? But we don't know how to take the antiderivative of this. So another way to do it is to make a slope field, which they already did, and then trace out the slopes that they tell you, and then that graph is the solution, right? But there's a lot of solutions, right? Because when you take an antiderivative, you get a plus c. So what information do you need before you can figure out what the c is? You need a point, right? You need the initial value. So if we're going to sketch a particular solution instead of the general solution, we need an initial value. So sketch the graph, the particular solution that goes through the point 3, 2. So on your graph there, find the point 3, 2. So you go over 3 and up 2, right? So then put a dot there. So sketch 3, 2 first. Put a dot there. And then from there, trace out to the left, following all the slopes. And then trace out to the right, following all the slopes. It's a little bit tricky, but give it a shot. So whenever you get to a little line, it tells you where to go. It points you in the direction you're supposed to go from there. Slope is a curve, where you go, right? It's the direction. This point here, kind of falls back, and then it tells you to go that way, and then when you get here, it kind of flattens out, and then also it tells you to go this way. That's it. Make sense? Yeah. Yeah, I mean, it's not an exact science. I would say that you're not over here, it should be simple. So you have your crossing through a line, you should be more following. But yeah. Make sense? You do it on your own next time, maybe. If not, ask some questions. So then you can actually trace that out. So there, George, you've been immortalized in the video. 50 years from now, I'll still be teaching. And George Grow II will be in calculus. And I'll say, that was your dad's answer. Crazy. I'll still be here. It's crazy. That's what's crazy. Okay, now for example 5, which of the slope fields pictured match dy dx equals xy? Okay, so first of all, you see the multiple choice. You got A, B, C, D. We got to pick the right one that goes with this. So first thing I want to talk about is the quadrants. In quadrant 1, the x is positive and the y is positive. So that means when we figured out our slope, we'd be taking a positive number times a positive number. And a positive times a positive is positive. So that means for the correct choice, in the first quadrant, the slope should be positive. So that eliminates b, right? Because in quadrant 1, for the b graph, there are some negative slopes. Everybody good? So b is out. Okay, then in quadrant 2, you have a negative and then a negative x and a positive y. And so then you'd have a negative times a positive when you figured out the slope. So the slope would be negative. So in quadrant 2, which of these have negative slopes? Unfortunately, A, C, and D all do. But at least we got rid of B, thinking about it this way. Okay, now let's think about what would happen on the y-axis. On the y-axis, the point is something, comma, or 0, comma, something, right? On the y-axis, it's 0, comma, something. So if the x is 0, this slope would be 0, right? So on the y-axis, the slope should be 0. That eliminates c, because it's pretty steep at 0 in c. So now we're down to a and d. Is everybody still with me? Okay, now let's think about the x-axis. On the x-axis, the y is 0. So we'd still have a number times 0, which was still coming out. So on the y-axis, the slope should be 0. So that eliminates a, because it's pretty steep on the, I think I said the y-axis, I meant the x-axis. On the x-axis, the slope should be 0. So that eliminates a, because it's pretty steep at the x-axis for a. But the slope is 0 for d on the x-axis. Do you see that? It's pretty flat, close to 0. So that means it's 0 at the x-axis. So D is the answer. Is everybody okay with that? Are you sure? Okay, so there's some more numbers on this handout, 29, 30, 31, 32. Those, you can do some of your homework problems on this if you want. Or you can do it on your own sheet of paper, it doesn't matter. I just provided those extra dots for your homework problems if you'd like to use them. Not quite there yet, though. I still got one example. Kind of sounded like I'm sorry to get your hopes up. Bless you. So we're up to example 6. And for example 6, we're going to have a differential equation dy dx equals 1 over x. And first thing I want to comment about is there's a problem when x equals 0, right? Because you can't divide by 0. So I want to mention, though, that there's two possibilities. We know for sure that the slope doesn't exist at 0. But that doesn't necessarily mean that the point in the original graph doesn't exist at 0. Okay, so there are two possibilities. First possibility is the slope doesn't exist at x equals 0, but there is a point at x equals 0. how is that possible? How can a slope not exist, but there still be a point? There could be a corner point, a cusp, or a vertical tangent, right? Okay, but it is possible that the slope doesn't exist and there's also not even a point there. We can't tell necessarily from the differential equation. The differential equation is just about the slopes, so we can tell where the slope doesn't exist, but we can't necessarily tell where the point doesn't exist. Okay, so now we're going to make a slope field. For dy dx equals 1 over x. Now this slope field is not going to be super tough because it's only got an x in it, right? So when x is 1, the slope is 1. X is 1 at all of these points going up and down, right? So that means the slope is 1 at all those points. So I can just draw a 45-degree angle at all those locations. Then at x equals 2, the slope is a half. So for all these x values, for all these points, x is 2, so the slope's going to be less steep, a half instead. Now let me back up to a half. When x is a half, the slope is 2. So steeper in here. Now we can trace this out. What does that look like? Maybe, yes. Maybe a vertical tangent, but I'm talking about what graph is this? It kind of is it kind of looks like square root, except square root doesn't have it starts at 0, 0 and has a nice slope there. It's natural log of x. Of course it's natural log of x. The antiderivative of that is natural log, right? Okay, now what happens back here? At -1, when x is -1, the slope is -1. So along all those x's, draw a little tick mark that has a slope of -1. Because 1 divided by -1 is -1, right? Okay, then at -2, the slope is -0.5. So still negative slope, but not quite as steep. So what's going on is, it looks like this on that side, and it looks like this on that side. So now I just graphed the particular solution, right? So maybe that was part B. I just don't want you to get confused. When I graphed in, that wasn't the slope field. The slope field was just the tick marks. But then when I connected them, I was solving for what y is. And that's the particular solution, right? I guess instead of the, I should just say A, because there's a lot of particular solutions. Okay, so this is natural log of x, right? What's this? Natural log of negative x, or natural log of the opposite of x, right? So remember when we solved this last week, we got y equals natural log of x when x is greater than 0, but we got the natural log of the opposite of x when x was less than 0, right? What was the fancy way to say all of this? Natural log of the absolute value of x. Okay, so this is part C. Solve the differential equation. Should have plus C's in here, just got in a hurry a little bit. Probably wouldn't even mention that if I wasn't videoing. You get the idea, right? So just don't forget, when you take the antiderivative of 1 over x, don't forget to include your absolute values. That's just a reminder today. And it's gelling with what we did today, the slope field. So back to the original question, Carter, it was kind of looking like there might be a vertical tangent there, but it turns out that there's no point there. Natural log of 0 is not allowed. So we're on, it turned out that this was the case. But I want you to know that this could have been the case. There might be a different slope field that would connect out like this and then be a vertical tangent. Or there might be a different one that would have like a cusp or something. All right, thanks for listening.